In this tutorial, I'm going to show you how to set up a system of ODEs to solve a lumped parameter model and how to run it. And we're going to do this using a 0D only circuit. And so no multiscale. We're just going to do it on a 0D model. But then what you learn, the steps you learn, you can also apply later to a multiscale model if you couple the necessary flow and pressure to your 3D domain. And so we're going to start, we're just going to use a simple circuit right here. The circuit contains both capacitors and inductors, so then you can learn the necessary equations that go with these elements. And so later on you'll be able to construct your own model if you want a more complicated model. And so here's our circuit that we're going to work on. And in this circuit we have some inflow waveform that we're going to prescribe right here. And then we have a couple branches right here. You can think of these as the outlets of your multi-scale model. But in this 0D model, we have inflow that go into all these branches. And so we have the RP, the resistors RP 1 and 2 here, and then downstream resistors are RD 1, 2, 3. And then we have capacitors right here. And the pressure across the capacitor, so here's ground, the pressure across the capacitor here is X2, X3, and X4. And I'll explain why we use the labeling here later, you'll see. And then we have the flow across the inductor, that's our X5. So the X's are our variables that we want to solve in our ODEs. And then when you have the flow into the circuit, it produces some pressure. We're going to call this P in. Okay, and then here's the flows into these two branches, Q1 and Q2. And so in your system of equations, all these different elements, the resistors are very simple elements that is not dependent on time. It just depends on the pressure drop across the resistors, just depends on how much flow is going through it. So you do not need a differential equation to describe a resistor. But for any element that behave in such a way that's dependent on time, where you need a differential equation to describe the element, you need to assign a variable in your circuit to solve for that element. And so in this case, we have all of the capacitor and inductor elements need to have a equation that describes it. The equation that describe a capacitor and inductor are right here. So for a capacitor, the amount of flow that's going into the capacitor is dependent on the capacitance value and the pressure drop, the change in pressure over time across the capacitor. And for the inductor, the pressure drop across the inductor is dependent on the inductance value of the inductor and the change of the flow that's flowing through the inductor. And we can arrange these equations to give us something like this. So these are now the differential equations that we want to work with, where it says that dp dt, the pressure change for a capacitor is the flow into the capacitor divided by capacitance, and so on for the inductor. And so I'll talk about how we're going to set up the system of equations now for this circuit. And so we'll go one by one for the different elements. So if we look at the element number 2, so looking at this capacitor right here, so we're trying to apply this equation to this element right here. And so the dp dt is our dx2 dt. So remember, x2 is the pressure right here at this point. And so dx dt is the change of pressure over time, so that corresponds to the dp dt here. And so this is equal to this expression right here. And what this expression is this expression right here, is the flow that's going to the capacitor divided by the capacitance. And so here's our capacitance right here, and then this expression here tells you what the flow is that's going into the capacitor. So your capacitor is here, your Q1 is going this way, and so the flow that's going into the capacitor is this flow. So when you have flow that goes in here, the only two places it can go is either into the capacitor or down this way. And so if you want to find out the flow that's going into the capacitor, then what it is this flow minus this flow, then it's the flow that you want. And so here we have Q1 minus this pressure divided by RD gives you this flow. And so that's the equation for this element right here. And for this element, it's equivalent. It's pretty much exactly the same. I'll let you figure out what that is. You can figure it out the same way as this equation. And then let's look at the inductor now. So that's the variable 5 that we're looking at. So for the inductor, we want to set up this equation where the change in flow in time is equal to the pressure drop across the inductor divided by the inductance. So x5 here, this variable is the flow. Okay, that's how we defined it, is the flow through the inductor. And so the change in flow is dx5 over dt is equal to the same as this expression. So we have the L at the bottom here, and the top, what we want is the pressure drop across the inductor. So which is the pressure drop across here. This pressure is P in, this pressure x4. So that's the expression that we want. And then for this capacitor, you can kind of go through it and figure out why that's the way it is. Here's our dp dt, and then here's our capacitance. This is the flow that's going into the capacitor, which is this flow minus this flow, and this flow is just x5, and then that flow is this pressure divided by RD3. Okay, so here's our system of equation, minus 1, that you can figure it out yourself. And then one more thing that we need to solve is ultimately we want to solve for this pressure, right? And so now this pressure right now is not really appearing in a lot of these equations, and we need to solve for the pressure on its own. And so the way that we do that is we need to solve another equation that describes the conservation of flow, and by doing that we can solve for this pressure. And the way we do that is that we say that we set up the equation that says the flow that's going in here has to be the sum of all these three flows, right? That's the conservation of flow right there. So that's this equation, and then we can replace these two things. We know how to calculate Q1, Q2. That's just the pressure drop across the resistance divided by the resistance, and so we replace these two terms. And then now you have this equation, then you can simplify this equation to get your P in. Okay, so that's an overview of the mathematical side of things. You might have to kind of go through this a couple times if you don't know how to solve ODE, how to set up an ODE system for a circuit. You might have to just review this a couple times to be able to get it. But let's just say you've got that, and now I'm going to show you how we're going to run this system of ODEs and how to solve it and how to run it to get the results that we want. And so I'm going to use this program that I wrote, and I've included it with this tutorial. What this program does is it solves the system of ODEs using an RK4 algorithm, and here I'm going to show you how to use it. So you open this this program, and the first thing you need to set is you need to set how many variables you want to solve. We have 7 right here. Well, in this diagram we only have 4, but we have a couple additional ones just for housekeeping purposes. So we need one of them that we use to keep time, and then if you want to print out additional results, then that's going to take up a spot for the variables that you want to use in this program. So I'm just going to set it at 7 right now, and you'll see why. But you need at least as many as you have variables. And then here you can kind of set what the time step size you want to use, how many time steps you want to simulate, and how often you want to save the results. Usually you don't have to change this. Right now it's set to simulate probably enough time for what you need, and then it's saving every 0.01 seconds. And then you don't have to do anything here. You can. Okay, so the stuff that you want to add starts after this line right here. Okay, so here you're declaring a couple variables or just a couple parameters that you want to use, and depending on what you have in your circuit, you can figure out what variables you need and you could declare them here. And then right here we're going to include the values for these elements. I'm just going to do it in a separate file just to keep things clean. If you want, you can just put it right here, but I'm going to do it on this in a separate file. And I'll show you what that file looks like. It's called this file right here. I'll just drag it right here. Okay, so in this file, you're just setting all the parameter values for your RP and for your capacitances and RDs. So you have two RPs, and then so you have an array of two elements here, and then you set the values of the R's right here. And you have three capacitances, so you put the values here. The D is just the it's the 10 to the power of whatever. And so, and then here's your value for the L. And I have pi right here just so that you can use it if you wanted to. You can modify this file depending on if you have different elements you want to set their values using this format. You need to follow the format pretty much exactly, otherwise it's not going to work. So that means you need to take care of the number of spaces here. You need to use the same number of spaces. You need to pay attention to which of these lines need a comma. The last one does not have a comma. If it does, then it's not going to work. So just you have to pay attention to the formatting here. But anyway, in this file, you set all your parameter values. Okay, and then it's in here. It's included in this file here. Okay, so and then this is, you don't have to change this. This is the variable that we're using to keep time. So we're using the first variable x1 as our time variable to keep time. And then here you set your cardiac period. So here we have 1 second. So this is 60 beats per minute. And then this variable here you're going to use to calculate at what point of the cardiac cycle you are. And so you're doing a modulus of the time to your cardiac period. So I guess the only thing here you have to change is your cardiac cycle. If you have a different heart rate, then you want to change this value. And then, so as we talked about, we're setting in our circuit, we have a inflow waveform. So here's I have a flow waveform here calculated using Fourier transform, and I've covered this, how to do this, in a previous video tutorial. So if you don't know how to do that, you can go back and review that. I should change this comment right here. So this is our flow waveform. Okay, so now we've got our flow waveform that's in this variable qin right here. So now we can use it, right? Now that we've defined what it is. And then remember what we talked about calculating this Pin right here based on this equation. So you solve this equation, solve for Pin, and then you figure out what Pin is, and you enter it right here. So you could take a look at this expression, but you'll find that it's equal to whatever you solve here for Pn. And then we're going to use these Q variables, so we're just going to calculate them, and they're very easy because they're just defined by the resistance equation right here. It's just the flow across the resistor. And so we define Q1 and Q2 with this line right here, and you could take a look to see if it makes sense. And now we're going to enter the ODEs. And I suppose before I go on, I'll explain a little bit of how you use the variables. So this program is calculating these equations for every time step that you run it. And so at any given time, it stores an X array, which are basically the values of your variables that you're trying to solve at any given time. And so you can actually directly use these values to calculate the dx dt in your system of equations. And so for the x variables right now, we have x1 to x7 because we said that there's 7 variables, so you could directly use these variables. And then the f array contains basically the answers to your differential equation. And so, for example, your f4 would be your dx4 dt, the value of your dx4 dt at this particular time step. And what that is described by this equation. And so you could directly use the equation to assign your f array. And that's exactly what we have done here, is that we've set the f2 to 5 based on these equations that we calculated before. And then lastly, we have, like as I said before, we had a couple additional x variables for housekeeping purposes, and we have 2 additional. Remember, we only have 4 things we have to solve, and then we use 1 for keeping time, and so we have 2 more left that we can use. And the way that I'm using it is that I'm using it to print out these 2 additional variables. So remember, in the equations that we set up, Qin and Pin are not one of the variables that we're solving. And so this program will only print the x variables in the results. So if we want to get these waveforms as one of the outputs, we need to print them. And so in order to print them, we need to set them as one of the variables. And so we created 2 additional variables just for the purpose of printing these things. And if you just want to print something directly to a variable, you basically just set the variable to the value of these things. Okay, so that's how you would set up this program. And one more thing that you need to do is that you need to set, this program is solving a system of ODEs, which means you need a set of initial values for your variables. And those are stored in this file right here called init_vals. So you can go in here and then you can change your initial values. So basically, we have seven variables, so we need 7 initial values. And if it's an open loop circuit like this, what the initial values are actually don't change your results. And so you could set whatever you want. You could just put all zeros if you wanted to. I put some non-zero numbers just so that the simulation will converge faster. So it doesn't have to take as much time to go from 0 to what it's supposed to be. And so now you've set up everything that you need to basically solve this circuit. And what that means is that you have a known input flow waveform, and you have knowledge about what these parameter values are for the elements, and you have knowledge about how this circuit is set up so that you could run the simulation. You could calculate the flow and pressure in this circuit over time and see what this pressure waveform will look like over time. Okay, because these equations only tell you what the pressure and the flow are relative to each other at any specific instant in time. So what this program will do is it will step through thousands of steps to do these calculations so that it will produce results that show you what the waveforms look like in these elements for the pressure and the flow. So we've got everything set up, and now we just need to run the program. And so we go to the folder here, and we compile the program that we wrote. You could use any compiler. I'm going to use ITE4, but you can use any Fortran compiler. Okay, so now it's compiled. Now we run it. It's got a file called a.out that's created. So we run it, and now it's finished running. The program will print a file. It will create a file with all the results in it. It's called all data. So the structure of this file is very simple. It's got a bunch of columns. Each column represents the result of one of your x variables, and then the rows are just your time steps. So right now it's set to save results every 0.01 seconds, and so that's your results over time. So you could just load this in MATLAB or in whatever other program that you want to analyze this. That's how you run a system of ODEs for a lumped parameter network. Now, if you want to, so that was 0D model only. If you want to use this now in a multiscale simulation, it's very simple. You can put in a three-dimensional model in the circuit, and you could couple the pressure and the flow that you calculated using the lump parameter. You can couple that into your 3D model and be able to run a multi-scale simulation. And the way that this program is written is actually, for the most part, compatible with GenBC. And so you can copy this whole section here into the user.f in GenBC, and you'll be able to run a multi-scale simulation with that. But you'll have to make a couple changes to couple the pressure and the flow properly. But for the most part, you'll be able to use what you developed for this program for the LPN standalone simulation in a multi-scale simulation.